Let us now look into the difference between BJT and FET. So as we all know, BJT is a bijunction transistor and FET is field effect transistor. And when you look in terms of operation, how does it operate? Basically, BJTs are current control devices. So if you check with your analog electronics, the entire operation of the BJT characteristics is controlled with the help of current. Like it can be the base current or the collector current or the emitter current. So basically they are current control devices. And when you look into FETs, you can also observe they are voltage control devices. They are the voltage is dominant in FET. For example, VDS or VGS, these are the voltages with respective to the drain and source and gate and source coming into comparison with BJT, and therefore it is a voltage controlled device. And at the same time you check with the second parameter called as input impedance, that is how much is the resistance offered at the input side. So BJTs offer small input impedance. That means very low resistance is offered at the input side, and as a result it can damage the device. Whereas when you look into the FET, they offer greater input impedance than BJT. This means they are practically drawing no current and therefore do not load down the power circuits that's feeding it. So BJT is more safer in terms of resistance offered compared to BJT. Then we have the gain. BJT offers greater gain at the output than FETs, whereas in terms of FET, the gain is smaller than BJT. Size, yes, comparatively FET are smaller sizes than the BJT. BJT are quite bigger in size, FET is smaller in size. Popularity, BJTs are very less popular and are less widely used until the advent of FETs. And FETs are definitely more popular because they are more competitive than the BJT, and most of the applications FETs are used. Cost, BJTs are quite comparatively lesser price of FET, and FETs are expensive, but still the effect of FETs are more strong and dominant than the BJTs. Now we look into the brief history. So this history is considered from the advent of ICs. So in 1958, Jack Kilby, please remember Jack Kilby was the first person who came up with the concept of IC. So first integrated flip-flop with two transistors at Texas Instruments. So way back in the late 50s, IC was found by Jack Kilby. In 2008, Intel's Itanium microprocessor contained more than 2 billion transistors. So initially, this concept of IC was developed with the help of just two transistors. Remember, small scale integration with only 10 devices, less than 10 in this case, two transistors. So right now in 2008, we have 2 billion transistors and a 16 GB flash memory. So how much drastically the growth has occurred in terms of fabrication. So contain more than 4 billion transistors. So we are in this age of very large scale integration. So this corresponds to a compound annual growth rate. Yes, this is how the growth is going on. It's almost double, 50%. That is how initially it started, and it for 50 years this is an incredible growth. So this has happened only because of the miniaturization of transistors and how improvement in manufacturing industry. That is nothing but your fabrication procedures. However, as transistors become smaller, they also become faster, dissipate less power and are cheaper. Yes, what is the intention of going for a smaller size? The lesser the size, lesser the power consumption, lesser the power dissipation, so smaller is the size, and as a result speed is more. So many parameters are coming into picture, and as a result most of the sizes are considered to be small, and advantage is also huge. So, and like this, the history went on with more ideas coming forth, and 10 years later, Jack Kilby, he himself at Texas Instruments realized what is the potential on building on a single piece of silicon. And as a result, way back in 56, that is just before IC's invention, these three people who were responsible for the invention of transistor received the Nobel Prize, but whereas Kilby, who came up with the technology in the year 1958, got the Nobel Prize in the year 2000. for the invention of integrated circuits or ICs. So nobody knows what was the reason, but at least he had a recognition at least later. So this is how we find the importance of ICs. Transistors are electrically controlled switches. So we all know transistor is nothing but merely a switch. So in Bell Labs, BJT was developed, which was more reliable, less noisy, more power efficient way back. And early ICs primarily used BJT. Yes, BJTs were used inside the ICs because they were able to switch to much larger currents between emitter and collector. As I told you, BJT is a current controlled device. So way back in 58 ICs came, and then transistors were used, and gradually in the year 1960s MOS technology came into existence, that is metal oxide semiconductor field effect transistors. So what exactly MOSFETs did was they drew zero current when idle, that is when there is no working principle, they don't draw any power, and as a result they don't give up any current, and as a result zero power dissipation, whereas BJTs are not like that. So that was the advantage of MOSFETs. And there are two types of MOSFETs, NMOS and PMOS. And why is it called as NMOS and PMOS? Because of the type in which they are constructed, they are fabricated. NMOS transistor is the one which is constructed on a P substrate. PMOS is the one which is constructed on a N substrate. So gradually you will get to know about the difference, what is NMOS and PMOS. So this is a brief history based on MOSFETs, and we still go on with this. After NMOS and PMOS device, we come up with something else, new topic, which is called right now, way back in the 60s or 70s, we call it as the CMOS technology. So in 63 itself, in the early 60s, they came up with MOSFETs at 62, and then eventually they came up with something called as CMOS. So what is CMOS? It is combination of both NMOS and PMOS being used, and complementary. Why complementary? When you look with NMOS and PMOS, in NMOS you have a device which is constructed on P substrate, and electrons are the majority charge carriers, whereas in PMOS is constructed on an N substrate, and as a result holes are the majority charge carriers. So both are complementary in action. Here electrons works, here holes works, and if this works in negative voltage, this works in positive voltage. So each and every aspect, NMOS and PMOS are complementary. They are in terms of reverse working principle, and therefore the combination of these two is called as complementary metal oxide device. So these circuits used transistors but consumed only nanowatts of power. I just now told you about CMOS technology. It is consuming very less power, and 6 orders of magnitude lesser than bipolar counterparts. So when you compare with respective to BJT technology, it is 6 orders lesser, smaller size than the BJT. So with the development of silicon planar process, MOS integrated circuits became attractive for their low cost, because each transistor occupied less area and the fabrication process was simpler. Yes, there were many advantages for considering the growth of MOSFET comparatively with BJT. Fabrication was easy and it occupied less space, lesser area, and as a result power consumption also was very less, power dissipation in the form of heat also was very less, and comparatively the size and the cost was lesser. So and that is how the MOSFETs grew drastically. So basically, what is a MOS transistor? So we should first understand the fact that why the name metal oxide semiconductor. Please understand metal you can see here, metal oxide semiconductor. So this is a layered structure. This is a layered structure, and initially you find the metal. So the metal, whatever the metal you are using, that will be considered here. Next you have the oxide. Oxide is okay. Oxide is just when you expose that layer, you call it as oxide. The layer, when it is exposed to oxygen or air, the oxygen molecules combine with the layer and they form the oxide. And finally you have the semiconductor. So semiconductor can either be N type or P type. So normally the semiconductor is silicon. So using silicon and germanium, it is possible for us to construct N type or P type. So when you look into this, you have the semiconductor. The semiconductor here is nothing but the N type or P type, and N type or P type is considered here as a base, and that is why it is called as a substrate. So on this substrate, so if you take it as P substrate, and counterpart here will be one more diagram which can be constructed using N substrate, and in place of N you would have P. So in place of P substrate you would have N type. So when you have this, and this P is nothing but again semiconductor, when this is exposed to air, the oxygen molecules will combine with this, and as a result they will form an oxide. And since it is silicon, silicon combined with oxide will give you SiO2. So you have the metal, you have the semiconductor, you have the metal, and you have the semiconductor and you have the oxide. Above the oxide you apply a layer of metal, and the appropriate metal applied here is called as the polysilicon, which is another version of silicon itself, which exhibits the metallic properties, and that in fact behaves here as a gate. So metal is normally the polysilicon, and that is the reason we have MOS, MOSFET. So MOSFET is a layered structure with metal behaving as the polysilicon, oxide is nothing but the silicon oxide or silicon dioxide, and then you have the silicon as a substrate. So when you look into this, metal is conducting. Semiconductor also conducts at times, but still we will consider it as a conducting layer. This metal is also a conducting layer. So you have two conducting layers. In between you have an oxide. Oxide is nothing but behaving as an insulator. So please keep in mind, sometime later I may tell you that the two layers which are conducting and in between you have an insulator is nothing but a capacitor. So this is how we can assume. So you can have like this. So this is your metal, this is your semiconductor, and in between you have your oxide. So what is this device? This is nothing but your capacitor. Doesn't it look like a capacitor? Two parallel plates filled with an insulator. So the insulator here is the oxide. It is the oxide, and this one layer here behaves as your metal, which is polysilicon, and in the bottom you have the semiconductor, which is S. Therefore we have MOS or the MOSFET. So this is how we see the cross section, and counterpart of this is your MOS structure, but still I can conclude that telling that this is your NMOS device. As I have already told you, you have to have a substrate, right? So substrate is the basic material. Here you have P substrate. So right now let me take it as N substrate. So this is of N type, and I have to appropriately find out the diffusion area. So this becomes your P type. So this becomes your P type, and above this you have your oxide. Above this you have your oxide. Above this you have your gate. So this forms your PMOS device. So this forms your PMOS device. So this is how an NMOS and a PMOS device is differentiated. This is your NMOS, which is constructed on a P substrate. This is your PMOS, which is constructed on an N substrate. So you have PMOS, P diffusion, and when you look into this, these three, P, N, P, they form a junction. They form a transistor. So this is how a MOS transistor works. So as I have already told you, FETs, there are two types, enhancement mode and depletion mode. And again in both of them you have two types, which is PMOS and NMOS. So in enhancement mode, enhancement mode transistor, channel is going to form after giving an appropriate positive gate voltage. So please remember, simple enhancement mode, no channel. Depletion mode, channel is there. So if ever you want to create a channel, you have to give appropriate positive gate voltage, that is VGS. Voltage at the gate terminal is called as VG, V suffix GS. S is nothing but your source, or it can also be connected to substrate. Both source and substrate are grounded, which is at lower potential. Gate is always kept at higher potential, therefore it is given as VGS. So when you give positive gate voltage, it can create a channel, and that is how a channel gets created in enhancement mode. But during fabrication, there is no channel in enhancement mode. In depletion mode, channel will be present by the implant, that is during fabrication itself. However, if you want to remove the channel, you have to give appropriate negative gate voltage. So because enhancement and depletion also partially are complementary in actions, and therefore not much is discussed with respect to depletion mode. All the concepts are understood with respect to enhancement mode. So briefly I am telling you about how enhancement means no channel, depletion means there is a channel. Metal oxide semiconductor advantages. What are the advantages of FET over BJT? FET is a unipolar device. So there is only one type of charge carrier which is present, majority charge carrier. Either the current conduction happens because of the holes or the electrons. Whereas in BJT, both of them will be conducting. Holes also will be conducting, electrons also will be conducting. They are bipolar devices. So that is one of the difference between BJT and FET. BJT is current control device, FET is voltage control device. FET has very high input impedance, so the device is safe. Whenever you are using FET, your input side is safe. It is having an input impedance of 109 to 1,000 ohms. Source and drain are interchangeable in most of the low frequency applications. Low voltage, low current operation, less noisy, no minority carrier storage, very small in size. So obviously when you compare them both, it is very advantageous than the BJT. So this is the symbolic representation of FETs. So when you look into this, three terminals are there. One is the drain, one is the source, and the other one is the gate. So this is your NMOS. And so now the differentiation goes. Right now I am talking in terms of enhancement only. Please remember, this is enhancement mode device. NMOS transistor has the representation of gate, drain and source. PMOS, they are complementary, right? So therefore I have to show a bubble at the gate. At the gate you always see a bubble, a not symbol. So this is the representation of PMOS. And how does it work? When gate is equal to 0, it is merely a switch. So it is a switch representation. You have the drain terminal, you have the source terminal. Gate can be opened and closed. So when gate is equal to 0, it is an open circuit. When gate is equal to 1, it is a closed circuit. So whatever is present at the drain will flow to the source. There is a short. Whereas here there is an open circuit. Whatever is at the drain will not flow to the source. In PMOS it is complementary. So when G is equal to 0, gate is equal to 0, in NMOS it is an open circuit, whereas in PMOS it is on. How? Since gate is equal to 0 and there is a bubble here. Bubble is nothing but 0 bar. It becomes high. So gate is on. Therefore it becomes a short circuit. When gate is equal to 1 bar becomes 0. Therefore it becomes an open circuit. So this is how the representation of the NMOS and transistor devices are shown in the form of switches. And this is the CMOS device, CMOS inverter. So as I have shown you, please notice here, you have this as your NMOS, no bubble, and this is your PMOS. So this is your N-type device, and on the top you have your PMOS device. Why it is PMOS? Because there is a bubble here. So combination of N and P together is called as CMOS, and P is normally placed on the P is normally placed in the pull-up region. So whichever region is near to VDD supply is called as pull-up region. Whichever region is near to ground is called as pull-down region. So always by default in CMOS you have the PMOS on the top, NMOS in the bottom. We'll gradually continue with the remaining classes shortly.